This is lecture 3F1 for Calculus 1. I'm calling it a roadmap. I'm calling it a roadmap because I hope it's, in some small way, an overview for what we're trying to do in this class. I think at some point with all these derivations and epsilons and deltas and taking all these limits, it's kind of a forest in the trees problem, so hopefully this gives you a view of the forest. Right. So what we're doing is looking at several operations or attributes of functions. Those would be limits, continuity, derivatives, and the integrals. That happens later in the chapter, or later in the book. So limits, continuity, derivatives, and integrals. All of these are applied to functions. However, the functions are subject to certain operations. You can take linear combinations of functions. That means you multiply them by constants and add them together. You can multiply them. You can divide them, you can compose functions, and you can raise a function to roots and powers. Most of the work in this class is figuring out how the limits, continuity, derivatives, and integrals apply to the functions under linear combinations, multiplication, division, composition, and roots and powers. Once we figure out how these apply, we call them the limit laws, or the rules for continuity, or the rules for taking derivatives. Okay, so I'm summarizing the results on the next chart. And on the next chart, say that f and g are continuous and that the limit of f is L and the limit of g is M. So here are the operations. Here is taking a linear combination of functions. Alpha and beta, say, are constants, and you're just adding alpha f plus beta g, arbitrary constants. Okay, then there's multiplication of functions, division of functions. Of course, you can't divide by 0, you know that. And composition, and taking a function to some root or power. If we look at each heading, limits, continuity, and derivatives. Under limits, if you have a linear combination of functions, you just take a linear combination of the limits, alpha L plus beta M. If you multiply the functions, multiply the limits. If you divide the function, divide the limits. If you raise the function to a power, raise the limit to a power or to a root. Okay, how about for continuity? The functions were originally continuous. Linear combinations are continuous. Multiplication gives you a continuous result. Division is continuous. Composition is continuous. Roots and powers are continuous. You do have to watch the domains because those will change. You need to take the intersection of the domains of f and g and maybe make some other conditions on them. But yes, continuity is inherited. Okay, and now derivatives. If you have a linear combination of functions, it's a linear combination of the derivatives. That's straightforward. But if you multiply the functions, you have to use the product rule. If you divide the functions, you have to use the quotient rule. I didn't write it out because I think there's an easier way to look at it than writing out that messy quotient rule. If you compose two functions and you want to take the derivative of the combination, you have to use the chain rule. For roots and powers, we already derived that. So these are the rules. For limits, all we did was establish that when you make these operations for the functions, you can apply the operations to the limits themselves. For continuity, things came straightforward. I think we proved continuity under composition and under multiplication. But when you take the derivatives, things look a little more complicated. Linear combinations, no problem. But multiplication, you need the product rule. Division, you need the quotient rule. Composition, you need the chain rule. Taking the limits or establishing continuity or taking derivatives really have a very computation-heavy basis. When you're working with limits, you have to deal with all those epsilon and deltas. Same with continuity. When you take the derivative, you either have to take the limit of those secant lines as they hopefully turn into the tangent line, or you have to take the derivative of the difference quotient. Right. But the idea here is that if we rigorously derive the limits, continuity, and derivatives for a few special cases, few special functions, and then we establish these laws, the limit laws, rules for continuity, and rules for taking the derivative, and later on rules for integrating, then things get much easier. All you have to do is apply those few special cases and these laws, and things turn into what is called plug and chug. By plug and chug, I mean you just look at a handbook or tables, you find out what the derivative or the or the integral is for a certain function, and you just make use of it with these laws. Right. Some people may have done that in the past with calculus, or perhaps you're going to do that in the future, but you don't have a basis for doing that unless you establish what we're doing here. And that's why we do all these derivations in this class. We're establishing the basis for this idea, and the idea is rigorously derive a few special cases, then establish certain laws, combine those few special cases and the laws to do all kind of problems. For the derivative, the few special cases we did were the power function, we looked at constants, then all those transcendental functions, the exponential, the sine, the hyperbolic sine, logarithms, and a few others. We also need to look at a few special, I put cases here, but I really mean conditions, because there's a contrast here between limits, continuity, and derivatives. And if you write them all down, you can kind of remember them a little bit. Okay, what happens if the limit is infinite? If you're taking a limit, there is no problem. In fact, we agree to say that the limit is infinite. Of course, we mean the function is either increasing or decreasing without bound, but we even, infinite limits are very much accepted under the idea of limits. And if it's at an interior point, we honor it with another name and call it a vertical asymptote. Okay, but when you move to continuity, an infinite limit is rejected. If the limit is infinite at a point, we say the function is discontinuous there. And when you're trying to take a derivative, if the limit is infinite, we say there is no derivative, or the derivative does not exist there. So infinity is accepted under limits, but not under continuity and not under derivatives. Okay, how about jumps? If there's a jump in the function, we say there's no limit, say it's discontinuous there, and there's no derivative. Wild oscillations, again, there's no limit, it's considered discontinuous, and there's no derivative. Right, so that's consistent. Now we get down to these cusps and corners. A cusp is a corner that you swoop up to, so the function would swoop up to it and have that point right there. Okay. So if you have a cusp or corner and you want to take the limit, there is no problem with it. The limit exists. The function is continuous there, but the derivative rejects corners and cusps. If you have a corner or cusp, it says there, we say the derivative does not exist there. So I'm going to repeat that. I'm going to summarize that again. Just a second here. That's the cursor. Okay, so here are the special conditions. The conditions of an infinite limit. For limits, that's fine, but continuity and derivatives reject that result. Jumps and wild oscillations, nobody likes them. There's no limit, it's discontinuous, and there's no derivative there. For corners and cusps, you have limits and continuity accepting a corner and cusp, but the derivative, there is no derivative at a corner or cusp. So here there's two that reject it. Okay. An infinite limit is rejected by continuity, it's rejected by derivative. Jumps and wild oscillations are rejected by everybody. Corners and cusps are rejected only by the derivative. Okay, so I hope this kind of gives a little bit of an overview. I'll try to do another roadmap in the chapter when we add integration to it.